Exponential functions versus logarithmic functions. How do they relate? So we're going to start out with a very basic exponential function like we did a few lessons ago. Y equals 2 to the x. So we know when we graph this basic exponential function, it has a y-intercept at 0, 1, and then the multiplier is 2. And if you go back to that basic formula, it's because this is really saying y equals 1 times 2 to the x. Also remember, any time you raise a base to the 0 power, we get 1. So then to create our other points, as we move right 1, we would just multiply by 2. So 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. If we went the opposite direction, we would half. Half of 1 is a half. Half of a half is a fourth. Half of a fourth is an eighth. And we graphed this very basic function, y equals 2 to the x, a few lessons ago. We also graphed y equals 3 to the x and a few other functions. Let's talk about a few key features of this function. One is that it has a y-intercept at 0, 1. We wouldn't talk about the x-intercept because it doesn't have one. The domain is all real numbers. And we can also write that as you can just put your real number system, in like this. The range is from 0 to infinity, not including 0. So the range is all real positive numbers. It has a horizontal asymptote at y equals 0. And we're going to start talking about the end behavior a little bit. This is something we're going to start getting into. The end behavior is what happens as x gets really, really big in the negative direction and in the positive direction. So we would say, as x approaches negative infinity, y approaches 0. Because as you keep going this way forever, the actual functional values just get closer and closer to 0, but they never actually get there. And to denote which side of 0, is it from the positive side or the negative side, we put a little plus in the air. And that means y approaches 0 from the positive side. And then we would say as x approaches infinity, y approaches infinity, because that's what it does. It goes off to infinity, it increases without bound. If we were to ask where this function's increasing, we would say over the domain of all real numbers. If we were asked where the function is decreasing, we would say never, because this one happens to be a growth function, so it never decreases. So what is a logarithmic function? Guys, the logarithmic function is the inverse of an exponential function. That's one of the big reasons why we learn about logarithmic functions. It's so that we can solve exponential equations and lots of other things, like they work with the Richter scale and other types of behaviors. So go ahead and put that in your notes. How do they relate? They are inverses. So let's go back to the knowledge we know about inverses from our previous unit. We know that everything that was x becomes y, and everything that was y becomes x. So I'm going to show you graphically what this logarithmic function would look like. I'm going to go ahead and graph our reflective line of y equals x, because we know a function and its inverse function should always reflect over the line y equals x. For every point we have on the original function, we should have the inverse point on the inverse function. So since this has a y-intercept at 0, 1, this is actually going to have an x-intercept of 1, 0. This function has the point 1, 2, so this is going to have 2, 1. This function has the point 2, 4, so this one's going to have 4, 2. This one has negative 1, 1/2, so this one's going to have 1/2, negative 1. And you can kind of see how that behavior continues. And that is a logarithmic function. So the x-intercept, let's write down some of the important key features we notice on this one. In this case, the x-intercept is 1, 0. It doesn't have a y-intercept. Its domain is now from 0 to infinity, where its range is from negative infinity to infinity. And that's the whole purpose of an inverse. Everything that was x becomes y. Everything that was y becomes x. A logarithmic function doesn't have a horizontal asymptote. Instead, it has a vertical asymptote. And in this case, that vertical asymptote is at x equals 0. So if I was to write end behavior for this one, it would switch around. Instead of saying as x goes to negative infinity, I would say as x goes to 0 from the positive side, y goes to negative infinity. As x goes to infinity, y goes to infinity. And that's kind of a hard concept because people are like, wait, it's going more to the right. And it is, but it keeps growing up as it goes. All right. So remember, to find an inverse, what we do is we switch x and y and we solve for y. So if we started out with the function y equals 2 to the x, we would have switched x and y. So that's x equals 2 to the y. And then when you solve for y, what you ultimately do is you change it to logarithmic form. Now, you're not going to understand this part right this moment, but you will in a few minutes. So it becomes y equals log base 2 of x. And that's what we've graphed right here. This is the function y equals 2 to the x. And this one is the function y equals log base 2 of x. And they are inverse functions. Okay, so how do we switch these back and forth? As crazy as this is how my high school teacher taught me how to do it, and it's just always stuck with me. If it's in exponential form, you have some base raised to an exponent equals an answer. Then when you change it to logarithmic form, it becomes log, the base becomes the subscript of the answer equals the exponent. And a good way, it's kind of like a little loop if you want to go back and forth. If I'm trying to go from exponential form to logarithmic form, I'd write log, then I put my base of my answer equals my exponent. It's kind of a little loop that spirals in. Where if I went from logarithmic form back to exponential form, it's the base to the exponent equals the answer. So the big thing I want you to understand here is, guys, logarithms are exponents. That's the whole point of learning about them, so we can solve for those exponents where we've had to use technology in the past. So going back to what I just showed you where I found the inverse, that's why once I got to x equals 2 to the y, to then solve for y was my exponent, and I put equals log, my base became the subscript, log base 2 of my answer x. So that's how I made it from that step to that step. All right, so what we're going to do now is we're going to practice just going back and forth because that's really important. So the first one we have 5 squared equals 25. What would that look like if we rewrote the equivalent logarithmic equation? We would say log base 5, so that's the little subscript, of 25 equals 2. Remember what I said over here. Logarithms are exponents. So if you are doing this correctly, your log should always be set equal to the exponent. All right, so looking at the next one, we'd say log, the base is 10, of the answer, which was 100,000, equals the exponent, 5. If we go to the third one, log base 8 of 1 equals 0. And I want to make sure you practice saying this too. Listen how I'm saying log, then I say base, and I say what the base is, of the answer equals the exponent. All right, so this one we're going to do backwards. We are given the logarithmic form, we want to change it to exponential form. So our base is always the subscript. So our base is 2. Our exponent is what it's equal to, which is -4, equals our answer, which is what we're taking the log of. That's that part inside, 1 over 16. And if you check that, that is correct. If you raise 2 to the -4 power, it becomes 1 over 16 because you do reciprocal of 1 over 2 to the 4th, and 2 to the 4th is 16. So looking at the next one, our base is 9, our exponent is 1/2, equals our answer, which is 3. That is also correct because 9 to the 1/2 is the same thing as saying the square root of 9, which is 3. All right, so for graphing basic logarithms, guys, you have to remember that they are the inverse of your basic exponential functions. So since every basic exponential function of the form y equals b raised to the x has a y-intercept at 0, 1, our logarithmic functions are always going to have an x-intercept of 1, 0. Then to get the other point on there, you have to think invertly, where when you always raise your base to the first power, you just have itself, so that switches around, so we're always going to have the point be 1. All right, so looking at this first one, it says graph. State the domain, the range, and the asymptote. Remember, anything we do inside the function affects it horizontally. Anything we do outside the function affects it vertically. So since we're subtracting 2 inside the function, what that tells us is we are going to shift this function right to. Well, a basic logarithm always has a vertical asymptote at x equals 0. Go back to your beginning. This happens to every basic logarithm. So if we shift it, it's going to shift that vertical asymptote if we shift left or right. So instead of our vertical asymptote being at x equals 0, it's now going to be at x equals 2. And then just like we did with our exponential functions, what I do is I then pretend that that is my y-axis. And so because this is a base 2, I think invertly. So I'm always going to have the point 1, 0, which again, I'm pretending that the dashed line is my y-axis and I'm working from there. And then because this is a base of 2, I have to think about my powers of 2 but invert them. So I'm going to have the point 2, 1 instead of 1, 2. I'm going to have the point 4, 2 instead of 2, 4. And if you need to help you out, you can always make a little table like this. If you have a hard time seeing it, you know, I'd have 0, 1, 1, 2, 2, 4, 3, 8. But when you go to graph your logarithmic function, you're inverting those points. So the function we're graphing would have the opposite. It would have 1, 0, and then 2, 1, and then 4, 2, and 8, 3. And of course, I'm doing that from pretending that dashed line is my y-axis. And that way it takes care of the shift at the same time. And there's our logarithmic function. It also asks us to state the domain and range. So we want to make sure we do that. So the domain would be from negative infinity, excuse me, let me rewind that. The domain would be from negative 2 to infinity, not including negative 2. The range would be from negative infinity to infinity. So logarithmic functions will never have a domain of all real numbers. There are very few functions that do not have a domain of all real numbers, and logarithms are one. And that's going to be really important when we start getting to log equations because they will have extraneous solutions. All right, try the next one. Pause the video. When you're finished, start the video back. So this one goes left 1 and down 2. So the left one gives us that vertical asymptote. Our vertical asymptote is going to be at x equals negative 1. But I also put a dashed line for down 2 because wherever we draw these dashed lines at, that's where we've shifted this graph to. So I'm going to pretend that that's our x and y axis. And this one has a base of 3. So I'm going to be doing the inverse points of y equals 3 to the x. So it's going to look like this. From my pretend origin I have right here, where these two dashed lines intersect, I'm going to have the point 1, 0, and then I'm going to have the point 3, 1. If I had room for it, my next point would have been 9, 2. And don't think I can fit that because that's 3, 6. If I did, it would be like right over here. And then again, just like your exponential functions, you just kind of go with the general shape. As long as you get a couple of points on there, you're good to go. So our domain for this one is going to be from negative 1 to infinity. Again, logarithmic functions do not have a domain of all real numbers. Our range is from negative infinity to infinity. And our vertical asymptote is at x equals negative 1. All right, so today we're going to do some very basic logarithmic equations, and then over the next few days we'll really step it up. So for these basic ones, what we're going to do is we're going to write the logarithmic equations as an exponential equation and then solve for the given variable. So this is where we're going to use the little loop from the previous page. Something else I want to remind you of, most of this stuff you should be able to do without a calculator, so I would brush up on your perfect squares and perfect cubes. Also powers of smaller numbers like 2 and 3, you should be able to recognize those patterns. Also recall from Math 2 where you learned about fractional exponents. Sometimes you're going to end up with a fractional exponent, and just remember that that's equivalent to a radical. So let's start with this first one. All right, so when it says log base 9 of x equals 3/2. When I rewrite that, the base is 9, the exponent is 3/2, equals the answer, which is x. Okay, well, there's two ways I can rewrite that. So that's why I wrote this up here. You can write that as the square root of 9 cubed, or you could write the square root of 9 and then cube it. Remember, the power is always the numerator, the index root is the denominator. So this is really saying the square root of 9. Well, I don't know about you, but if I don't have a calculator, I'd rather stick that cube on the outside than have to do 9 cubed and then take the square root. So let's make it easy on ourselves. So we know that the square root of 9 is 3. And then 3 cubed would ultimately give us 27. You can also do it using just exponent rules. When we get to 9 equals 3 halves, we know that 9 is 3 squared. When we raise a power to a power, we multiply. So 2 times 3 halves is ultimately just 3. So we have 3 cubed, and 3 cubed is 27. And that's just a personal preference. All right, let's look at the next one. So in this case, our base is 4, our exponent is y, and our answer is 256. So what we would need to do is break 256 back down. And this is why I was saying it's really important for you to know your perfect squares. Because if you know them, you would recognize that 256 is a special number. 256 is 16 squared. And so that's 16 times 16. And we know 16 is also a perfect square. It's 4 times 4 and 4 times 4. So we can rewrite this as 4 to the y is equal to 4 to the 4th power, because 256 is 4 to the 4th power. And then because the bases are the same, property of equality tells us that y is equal to 4. All right, looking at the third one, our base is x, our exponent is 4, our answer is 16. So we would take we would take the 4th root of each side, or raise each side to the 1/4 power to get x by itself, and we get that x is equal to 2. Because 2 to the 4th power is 16, therefore the 4th root of 16 is 2. And again, if you don't recognize that, you can go to the side, break down 16. That's 4 times 4, and then 4 is 2 times 2, 2 times 2. We would not put plus or minus on this one because you can't have a negative base. Remember your rules from where we learned about exponential functions. The base has to be positive and the base cannot equal 1. All right, so looking at the last one, our base is x, our exponent is 3 halves, equals 8. All right, so you can work this out using exponent rules, or you can work it out using radical rules. What I'm going to do first is I'm going to go ahead and raise each side to the 2/3 to get rid of that ugly fractional power on the x. So that gives us x is equal to 8 to the 2/3. And then if we want to change it to radical form, our root is the 3rd root, and then it's of 8 squared. So you can put the square on the inside, or you can put the square on the outside. Again, I feel like if you put it on the outside, it might be a little bit quicker. So we'd have x equals, the cube root of 8 is 2, and then 2 squared is 4. All right, so here's some basic properties of logarithms. So what you have to remember is a logarithm is an exponent. So when I look at this first one, log base b of 1, folks, anytime you see this, the answer is always going to be 0. And here's why. What that's really asking you when you say log base b of 1 is it's saying what power of b is 1. What would you raise b to? What's the only power you could raise some base to and end up getting 1? Well, the answer is 0. b to the 0 power is what gives us 1. Remember, a logarithm is equal to the exponent. So the same thing with the next one. Ourselves, what power of b would give us b? So obviously it would be the first power. b to the first power is what makes it equal to itself. Again, a logarithm is just an exponent. All right, when we get to number 3 and number 4, anytime you have log base b of b to the x, you ultimately just end up with x. And vice versa, if you have a base b raised to log base b of x, we ultimately get x. And the reason why is because they are inverses of each other. They undo each other. So when we substitute one inside the other, it's going to undo it. That's the whole purpose of an inverse. It's like when you have a square root and you're trying to solve for something, you would square each side. Or if you have x squared, you take the square root of each side. It's because they undo each other. And if you look at it right here, it makes sense, because if I do b raised to the x, I get b to the x. And the same thing over on the next one. All right, so let's apply these and do some problems. All right, all of these guys we should not be using our calculator for. We should be just able to read these and do this without a calculator. This is really, really important. So it says evaluate. Pretty much you're trying to find the exponent. So looking at this first one, it says log base 6 of 36. Really, that's just asking what power of 6 is equal to 36. And we know that the answer would be 2 because 6 squared equals 36. And if you want to write that right here under it, just so you kind of remember, that's why that is. Remember, we're finding what was that exponent on that base, which is the little subscript that would give us that answer. So the next one, same thing. 9 to what power equals 81? 9 to what power is equal to 81? Well, that's also 2, because we know that 9 squared is equal to 81. All right, so this one is actually that property that we were just talking about above. Anytime you take an exponential expression, and this part's the exponential expression, and you substitute it into a logarithm, and the bases are the same, they undo each other. So whenever you see something like this, it's like they cancel each other out, and the answer is just 10. So the logarithm undoes the exponential, and it's like they strip each other away, and we're just left with 10. So the next one's the opposite. The logarithm is substituted inside the exponential. So again, the exponential in this case undoes the logarithm. And it's like they just cancel each other out, so the answer is just 37. And this is why it's important to learn these properties, as weird as these functions are. All right, then we get to somewhere we may have to do a little work. So this is saying 27 to what power equals 1/3? Now, some of y'all may know the answer if you have really good number sense and you understand your powers and your fractional exponents extremely well. But for some of us, we may have to work that out. So what we're going to do is we're going to rewrite this. All right, the next step is we need to get these to be the same base, and we need them on the same playing field. So they either both need to be in the numerator or they both need to be in the denominator. So we can rewrite 27 as 3 cubed raised to the x. Then to get this 3 out of the denominator and back in the numerator, we can use our negative exponents. 1/3 is the same thing as 3 to the negative 1. Over here on the left side, power to a power, we multiply. So 3 to the 3x is equal to 3 to the negative 1. Now that we have the bases exactly the same, property of equality tells us that 3x equals negative 1. And then we would divide each side by 3, and we get x is equal to negative 1/3. And if you want to check that with your calculator, you will see that it works. If you raise 27 to the negative 1/3 power, you will get 1/3 because it's meaning the cube root of 27, and then because it's to the negative power, it does the reciprocal of it. All right, so I want y'all to pause the video and try F, G, and H. When you're finished, start the video back. Okay, so for F, some of y'all will be able to see this without work. 9 to what power gives us 3? Remember, this is all about exponents and powers. Well, the only way that was going to happen is if it was a fractional exponent. We know that the square root of 9 is 3. But if not, you can work it out just like we did the last one. You break it down to have the same base, work the way through, use property of equality, we get x is 1/2. The last two are those first two properties that we talked about above. Anytime you have log base b of 1, the answer is always 0. Anytime you have log base b of b, the answer is always 1. You can also work it out. 6 to what power gives us 1? 6 to the 0 power gives us 1, so the answer is 0. 7 to what power equals 7? 7 to the first power equals 7.